I'm going to describe a type of logic programming called axiomatic language. Axiomatic language has four main goals. The first, it is intended as a pure specification language. You tell the computer what to do without telling it how to do it. But this means you need a really smart implementation that can understand the user's specification and generate an efficient program. And many would say that that is wishful thinking. Second goal, we want the language to be minimal. Programming languages can be big and complex with lots of built-in features, or they can be small, and you add features by writing them in the language and providing them in a library. Axiomatic language follows that second philosophy to the extreme. Nothing is built in that can be defined. This means arithmetic is not built in because it can be logically defined. Now, we assume that a smart translator that can understand the user specifications will be able to recognize the definitions of arithmetic and map them to the machine hardware operations, so there should be no efficiency penalty. Now, the third goal is based on the observation that probably everyone in this room has a different view of what they want in a programming language. So if you're going to have a single ideal language, it needs to have the property of a metalanguage, a language in which you can define arbitrary language features and paradigms, which can then be used for software specification without leaving the original language. Such a language would effectively subsume other languages. And finally, we want the language to be beautiful, in the sense that Lisp is beautiful. Axiomatic language is based on the idea that the external behavior of a function or program, even an interactive program, can be specified by a static, infinite set of symbolic expressions that enumerate all possible inputs or sequences of inputs along with the corresponding outputs. For example, if you want to concatenate or specify the concatenation function, you could use expressions such as this, where you have your two sequence arguments and your concatenated result. So this is what that enumeration might look like. Initially, we give the case of two empty sequences and an empty result. And eventually in our enumeration, we'll get to this particular example of these two non-empty sequences and the concatenated result. So my argument is that that infinite set of symbolic expressions represents a specification of the concatenation function. Now suppose you want to specify a program that reads an input file and writes an output file. Well, that could be specified by expressions of this form, where input and output are symbolic representations of the files. So let's say we want to specify a sorting program that reads an input text file and writes the lines of text sorted. That could be specified by this enumeration. We first have the empty input text file, and the output file is also empty. And eventually in our enumeration, we have this particular three-line input file, and we give the corresponding sorted output file. Now in a moment, you'll see that these character strings are syntactic representations of abstract symbolic expressions which are interpreted to be lines of text. And my argument is that this infinite set of expressions specifies a sorting program, and it does it without giving a sorting algorithm. But what about an interactive program? How can a static set of expressions define an interactive program? Well, here we have a form of expressions where outs is a symbolic representation of 0 or more lines typed by the program, and in represents a single line typed by the user. So this expression gives us a particular execution history of this program. And if you have an infinite set of these expressions, for all possible execution histories based on all possible inputs that the user might type at any given point, then that set of expressions can be considered a specification of this interactive program. For example, you might want to specify a program that reads simple arithmetic expressions and writes out the result. Well, that could be done by an enumeration of expressions where one particular expression in the enumeration looks like this. The program writes out an introductory statement, then the user gives an arithmetic expression, program gives a result, user gives another arithmetic expression, program gives the result. Finally, the user gives a blank line which tells the program to halt, and the program writes out a final statement. So you would have an infinite set of these expressions for all possible inputs that the user might enter, including erroneous expressions. And my claim is that this infinite set, the static infinite set of expressions, is a specification of this interactive program. So if you accept that premise that programs can be defined by a set of expressions, then all we need from our specification language is that it be a formal system for defining these symbolic expressions of sets, or sets of symbolic expressions. The next few slides give the complete semantics of axiomatic language. In axiomatic language, a finite set of axioms generates a usually infinite set of valid expressions. An expression can be defined as, or is defined as, an atom, a primitive indivisible element, or an expression variable, or a sequence of 0 or more expressions and string variables. Syntactically, atoms are represented by symbols that begin with a backquote character. So the symbols you've seen earlier are not atoms, as you'll see in a minute. Expression and string variables begin with % and $, respectively. And sequences have Lisp syntax, a string of 0 or more expressions and string variables separated by blanks and enclosed in parentheses. An axiom consists of a conclusion expression and 0 or more condition expressions. And we use prologue-like syntax here where the conclusion expression comes first, followed by the condition expressions, which can be spread out over multiple lines. And comments begin with an exclamation point. Axioms generate axiom instances by the substitution of values for the expression and string variables. An expression variable can be replaced by an arbitrary expression, the same value replacing the same variable throughout the axiom. A string variable can be replaced by a string of 0 or more expressions and string variables. So here we have an example axiom. It has 2 expression variables, %x and %y, and then this string variable $. And we're going to replace the expression variable %x with the atom backquote x. And we do that there and here. We replace the expression variable %y with the empty sequence here. And the string variable $, gets replaced by the 2-element sequence, or 2-element string consisting of the atom backquote u and the expression variable %. And we do that here as well as here. So that is the variable substitution mechanism of axiomatic language. Axiom instances generate valid expressions by the simple rule that if all the conditions of an axiom instance are valid expressions, conclusion is a valid expression. And by default, the conclusion of an unconditional axiom instance, that is one without conditions, that conclusion is immediately a valid expression. So here is an example axiom set consisting of these 2 axioms, and here are instances of those axioms. The first axiom has no variables, so it just has itself as an instance. The second axiom has these 2 variables, So it has all sorts of instances, but there are just certain specific instances that are of interest here. This one, and that pattern continues. So these instances generate these valid expressions. The first instance has no conditions, so its conclusion is a valid expression. And then that valid expression matches the condition of this instance, so this conclusion is a valid expression. And now that valid expression matches the condition of this instance, so its conclusion is a valid expression. And that pattern continues indefinitely. So that is the inference mechanism of axiomatic language, and that is the complete semantics of axiomatic language. So here are some simple examples of natural numbers and their addition, where the natural numbers are represented in successor notation. These two axioms define our set of natural numbers, and the first axiom can be read as saying 0 is a natural number. The next axiom says that if something is a natural number, then the successor of that something is a natural number. And together these two axioms generate these valid expressions. The first one says that 0 is a natural number. The next one says the successor of 0 or 1 is a natural number. The next one says the successor of 0 or 2 is a natural number. And here we have two axioms for natural number addition. The first can be read as saying that if something is a natural number, then that something plus 0 gives you that something. The second one says that if argument 1 plus argument 2 gives argument 3, then argument 1 plus the successor of argument 2 gives the successor of argument 3. And these two axioms plus our natural number axioms generate these addition valid expressions which enumerate the addition function for all possible pairs of natural numbers. Now, the expressiveness of axiomatic language can be enhanced by adding these syntax extensions. A single character in single quotes is equivalent to writing this expression, which gives the character code using this sequence of bit atoms. A character string in single quotes within a sequence is equivalent to writing those characters separately in that sequence. A character string in double quotes is syntactic shorthand for the sequence of those characters. And finally, a symbol that does not begin with one of the special characters you've seen so far is syntactic shorthand for this expression, where you have this special atom that's represented just by the backquote character, and you have the symbol as a character string. And this is useful for decimal number representation, which is not built in. Here are some more examples of functions on sequences. The concatenation function we saw earlier is defined by this unconditional axiom. And these two, you'll notice these two string variables capture the contents of the argument sequences, and they're written, when you write them together in the result sequence, they effectively concatenate those contents together. So this axiom generates valid expressions such as this. Here we have an axiom which defines the membership relation, and that says that the first argument expression is a member of the second argument sequence, and it generates a valid expression such as this. Finally, we have these two axioms that define the reverse predicate or reverse relation, which says that the first argument is the reverse of the second argument. So here are the complete set of axioms for our sorting program we gave earlier. We need an ordering relation on character strings, and we define that first by defining a relation on expressions that can be distinguished by bit atoms. We need an ordering relation on the bit atoms, and then we need lexicographic ordering on sequences. And then we need a less than or equal to relation defined from our less than relation. And finally, we define this ordered predicate, which says that the elements of its argument sequence are ordered. Now we need a permutation relation, which says that argument 1 is a permutation of argument 2, And then we have these definitions of a set of characters and character strings. We first define the set of bit atoms, then the set of bit sequences, and then we define our set of characters, and we make use of this equal length relation, which says that the two argument sequences are of equal length. And finally, we define sequences of characters as character strings. And you may notice that the relation between bits and bit sequences is the same as the relation between characters and character strings or character sequences. And we could define a higher order form, in fact I did on the website, that generalizes that pattern, and then you could let these definitions be instances of that pattern. Now we need to define the set of text files, which are sequences of character strings. So we could use that higher order pattern here as well. Finally, the sorting function can be specified as a permutation that is ordered. And that's a nice specification that does not involve an algorithm. And then finally, we define our program expressions by specifying that the input file is a text file and that the output is sorted. Now the calculator program is more involved and it's defined on the website. In particular, the handling of invalid expressions is tricky, and I gave several options for that. Now the metalanguage claim for Axiomatic language is that it has the flexibility to define the semantics and approximate syntax of other languages. Here you have a single unconditional axiom that looks like code in a procedural programming language. Now on the website there are axioms that define this procedural language. So in combination they define the function that is being defined. They generate valid expressions for the function that is being defined here, such as this one that says that the factorial of 3 is 6. And the point of this is to show that this minimal logic programming language has the capability of defining a completely different language paradigm, which can then be used as a tool for software specification without leaving the language. And on the website, there's some examples of evaluating nested Lisp-like expressions. So some final comments. I think the examples show that specifications can be smaller and more readable than algorithmic code. And definitions should be more reusable than code that's constrained by efficiency. Axiomatic language has a great higher order capability in extracting common patterns and generalizing definitions. So the result should be greater programmer productivity. The Axiomatic language can be considered one of those tiny Turing-complete formal systems, but it retains human readability, expressiveness, and extensibility. The ambitious metalanguage claim is that Axiomatic language can incorporate the specification capabilities of other languages and thus subsume other languages. In a sense, it's the ultimate in customization. The programmer can customize the language to suit his or her taste, and you can customize the language for the problem. Specification by enumeration allows us to specify external behavior without defining internal operation, and it avoids the awkwardness of input-output in declarative languages. The extreme simplicity and purity of axiomatic language makes it well suited to proof, such as unfold-fold proofs. And this would be used to guarantee the correctness of your generated efficient program and with respect to the input specifications. But you still need to get your specifications right. But proof may be able to help you there too, because it may be possible to prove assertions about your specifications, such as proving that a security property is satisfied. And this could be more powerful than just testing. So there's a potential for improved software reliability. Now, the fly in the ointment is the extreme challenge of automatically transforming specifications to efficient programs. And when you mention that to people, often they chuckle. I think there's a consensus that that problem is not solvable, that programming inherently involves telling a computer how to do something. This can be considered a form of the old automatic programming problem. But in this case, the problem is more focused. You're not trying to understand natural language requirements. Instead, you're trying to recognize patterns and meaning in a formal language. Now, you can make an argument that no finite amount of knowledge can successfully transform all possible specifications that the user might write. But my hunch is that a manageable amount of knowledge may be able to transform straightforward specifications for most typical programs. So in this day of driverless cars and a computer that can play Jeopardy, I think this problem is doable and worth attacking. Thank you.